Today we're going to be talking about extreme values. Extreme values of a function on an interval are exactly what they sound like. They're just the maximum or minimum y values of that function on our interval. So if we take a look at this graph, we can find those values just by eyeballing. So for instance, if we're looking here, this is our maximum value of the graph because all other y values are smaller than it. So this is the biggest y value on this graph. Similarly, this will be our minimum of our function because it's the smallest y value that we see in our graph. The extreme value theorem tells us that if f is a continuous function on a closed interval, then it has a maximum and it has a minimum. Now there are two words I want you to pay attention to here. The first word is continuous. Why does f have to be a continuous function in order to definitely have a maximum and a minimum? Well, let's try drawing this graph again, but this time with a function that's not continuous. So we're going to keep our same basic pattern, but instead of this function being continuous, we're going to give it a break right here. So we've got our function, but we have a gap right where the maximum would be. This could be defined or not. Let's go ahead and maybe define it over here. So this is where we want the max to be, but it's not a max because we jump over it. We jump over that maximum value. This is why f has to be continuous, because if it's a continuous, we can guarantee that we're not accidentally jumping over our extrema. Similarly, we need to make sure that we are continuous on a closed interval. Why does our interval have to be closed? Well, if we have an open interval, let's not include one of these endpoints. Let's say this endpoint is open instead of closed, so we're not including that value. Well, this is where we want our minimum to be, but it's not a minimum because we're not ever quite reaching that point because that point is not included in the interval. So if we don't have a closed interval, we're not guaranteed to have a maximum and minimum. But if f is a continuous function on a closed interval, the extreme value theorem tells us that we definitely have a maximum and we definitely have a minimum. We can also think about local maxima and local minima. Sometimes this is also called relative maxima and relative minima. What does a local maximum mean? A local maximum is a point that would be a maximum if we zoomed in real close to it. So maybe it's not the biggest y value in the entire graph, but it's bigger than all of the y values around it. So this would be a local maximum because all of the other y values around it are smaller than it. Similarly, this is our local minima or local minimum because it is smaller than all the y values around it. It's not the absolute minimum, it's not the smallest in the entire graph, but it's the smallest in its little neighborhood. This is also a local minimum for the same reason. So let's think about what happens at the points where we have maxima and minima, whether they're local or they're absolute. What happens at those points? Let's ignore the endpoints for right now and just focus on the places where we have these humps. If we pay attention to what the slope is doing, at our maxima, we're moving from an increasing slope, a positive slope, to a negative slope. For our minima, we're moving from a negative slope to a positive slope. What happens as we move back and forth between negative and positive? We have to pass through zero. So the places where our slope or our derivative is zero are the places that we want to pay special attention to find our maximum and minimum. So this is leading us to an important definition. We want to pay extra attention to these places called critical values. A critical value is just where the derivative is zero or where it's undefined. Why are we paying attention to this? Again, that's where we're switching from an increasing to a decreasing slope or vice versa. So there might be an extrema there. What about undefined? Why do we care about undefined? If you remember the function for absolute value, looks like this. The absolute value had a cusp instead of a smooth curve. At that point, the derivative was undefined. So at cusps, we might also find ourselves a minima or a maxima. So we want to pay attention to critical values, which are the points where our derivative is either 0 or undefined, because we might find an extrema there. The point at which the derivative is 0 is called the critical point, or a critical point. Now, if f is defined on an open interval, then any extrema that it has is also a critical point. Why are we saying open intervals? Because then we don't have to worry about the endpoints, right? So if we don't have to worry about the endpoints, every single extrema that we have is going to have to occur when our slope is 0 or when our slope is undefined, because that's where we're switching from increasing to decreasing or vice versa. Now, something to notice about this theorem is that every single extrema is a critical point, but not every critical point is an extrema. So when we look at critical points, we are putting forth candidates for extrema, but we're not guaranteed that they are extrema. An example of this is if we have f of x equals x cubed. If we go ahead and take the derivative of that, this is going to equal 3x squared. So we have a critical point here at x equals 0, right? But if we look at x equals 0, that's definitely not an extrema, right? This is not a maximum or a minimum. So what happens here, this is a change in concavity. We'll talk about this later. But we found a candidate for our extrema, but when we look at the graph, we realize it's not actually an extrema. So again, if we're on an open interval, all of our extrema are at critical points, but not necessarily vice versa. Okay, so how do we go about actually finding our critical points? Well, the way that we do this is that we want to take a look both at our critical points and, if we're on a closed interval, our endpoints. In particular, we're just going to be talking about this with closed intervals. So what do we want to do? We want to check our endpoints. Then we want to find our critical values and check those. Our absolute minimum will be the smallest of those values we found, or of the y values that we found, and our absolute maximum will be the largest of the y values that we found. Let's give this a shot with an example. So for our first step, we're wanting to check our endpoints. Here we're finding the absolute extrema on f of x equals 2x cubed minus 3x squared plus 4 on the interval 0 to 3. So first we're going to check our endpoints. Our first endpoint is 0. So if we plug in 0 in for x, we get 4. And our other endpoint is 3. So if we plug in 3 in for x, we get 31. And you can just believe me on that or try plugging it into your calculator. All right. Now we want to find the critical values. How do we do this? Well, we want to find where the derivative is 0 or undefined. So let's start off with finding the derivative. We'll just use the power rule here to find our derivative, and we get 6x squared minus 6x. That's going to be our derivative. Now we want to set this equal to 0. And in order to find the values at which this would make us equal 0, we're going to go ahead and factor. So we can factor out a 6x, and we're left with 6x times x minus 1. So our critical points are going to be at x equals 0 and at x equals 1. All right, step 3. Now we want to check our critical values. We want to see what their y values are. We actually already did 0 because that was also an endpoint. We got 4. And if we plug in 1, we get, and again, this is into our original function, not to our determinant. If we plug in 1, we get 2 minus 3 plus 4, which is going to give us 3. All right, so we found all of our candidates for the x values for extrema, and we've plugged in those x values into our function to get the y values. Now we look at our y values, and the biggest one is going to be our maximum. So we have an absolute maximum where, well, our possibilities are 3, 4, and 31. 31 is clearly the biggest. So we have an absolute maximum at our endpoint 3, 31. And our minimum, if we look at our values, we had, again, 3, 4, and 31. So our minimum is going to be at our critical point 1, 3. All right, so we've now found our absolute maximum, absolute minimum on this function. So to recap, extreme values are just talking about maximums and minimums. Critical values are where our derivative is 0 or undefined, and those are important because they give us potential places for our extreme values. If we're on a closed interval with a continuous function, we definitely have a maximum and we definitely have a minimum. The way we find those is by checking the endpoints and checking the critical values to see which of our x values will give us the biggest and smallest y values.